It is Thursday, February 12th, 2026. And if you haven't glanced at a calendar lately, maybe take a second. It's worth just sort of, planting a flag in this moment. We are well and truly into the roaring 20s, the 2020s, I mean.
Yeah.
And looking at the world today, it feels profoundly different than it did just, 2 years ago?
It really does. There's been a definite shift. If you look at, the industrial landscape, the geopolitical map, even just the speed of the tech rollouts we've seen, February 2026 feels like a new chapter.
A new chapter, that's a good way to put it. It's not just a continuation.
No, something fundamental has changed.
Exactly. And a big reason for that, and the focus of our deep dive today, is that we are just a few weeks into the full execution of China's 15th five-year plan.
Right.
And I know I can almost hear the collective groan from everyone listening. The phrase five-year plan sounds so, bureaucratic.
It sounds like paperwork. It sounds like a committee meeting.
A meeting that absolutely could have been an email. That's what it sounds like.
It has that reputation, for sure.
But, and this is a really, really massive but, what we're seeing on the ground right now isn't about paperwork at all. It's what happens when the stuff of science fiction starts becoming factory floor reality. We aren't talking about vague, shiny predictions for 2050 anymore. We are talking about hardware that is literally rolling off production lines today.
Standards being written and enforced this summer.
Yes. And technology that is fundamentally reshaping the global economy, kind of right under our noses while we've been distracted by other things.
And that's the key distinction for this deep dive, I think. We need to ground all this excitement, because there is a lot of it. This isn't about, flying cars and cities in the sky.
Not yet, anyway.
Not yet. This is about deep structural economic shifts. It's about a concept that the sources keep coming back to: technological sovereignty.
Okay.
It's about a strategic move from a decades-long phase of catch-up, just trying to build what the West builds, to what you might call a fortress economy.
Fortress economics? That sounds pretty intense.
It is. I mean, think about what that implies. A supply chain where, from the lithium mine to the final microchip, everything is designed to be internal, resilient, and, frankly, shockingly advanced.
So it's about insulating an entire economy from the outside world.
From shocks. From geopolitical pressure, yes.
So today, that's what we're diving into. We've gone through a huge stack of sources, industry analysis from last month, reports from late 2025, even the draft text of some of these new technical standards. And the theme that just keeps screaming out is this pivot from innovation to application.
Right. That's the perfect way to frame it. The 0 to 1 phase, the pure invention, that's obviously important. But the 15th five-year plan is it's obsessed with 1 to 100.
1 to 100.
How do you scale it? How do you make it ridiculously cheap? How do you embed it into every single product and process? It's the difference between, inventing the internal combustion engine.
And building the Ford Model T assembly line.
Precisely. That is the mindset we're talking about.
Yeah. Okay, so we've got 4 huge areas to unpack today to really show what this means in practice. First up, what I think is the holy grail of energy: solid-state batteries.
And we're not talking about lab prototypes, we're talking production lines.
Exactly. Production lines running right now, and a new national standard that's going to change everything. Second, the silicon siege breakout. How China actually managed to bypass those huge export controls to achieve, independence in key areas.
It's a fascinating story, a bit of a workaround.
Then our third topic, AI gets a body, why the big strategic push has moved away from just building better chatbots and toward putting humanoid robots on factory floors.
Embodied AI, it's a huge priority.
And finally, we're going to look up to the high frontier. We're talking a water hunting hopper on the moon and building genuinely unhackable quantum communication networks.
It's a lot to get through.
It's a packed agenda.
Mm-hmm.
So let's start at the top, the strategic architecture of it all. The 15th five-year plan, 2026 to 2030, what's the headline?
The headline is a piece of jargon, but it's important. It's new quality productive forces.
Okay, let's unpack that immediately, because that is a buzzword if I've ever heard one. New quality productive forces. It sounds like something from a corporate retreat PowerPoint slide. What does it actually mean on the ground?
It's absolutely the buzzword of 2026, you're right. But it has a very specific meaning in these documents. It means the conscious integration of 3 things: digital tech, green tech, and advanced manufacturing.
So bits, watts, and atoms, all together.
All together as the primary engine of the economy. The leadership looked at the world, the trade frictions, the supply chain nightmares of the early 20s, and basically decided The old growth model is dead.
The old model being.
Pouring concrete, building more apartment blocks, more bridges. That can't drive growth forever. The new growth has to come from high-tech efficiency and self-reliance.
So it's about resilience. It really does sound like they're preparing for that siege you mentioned, but their strategy is to upgrade the castle walls with, like, laser cannons and a force field.
That's a perfect analogy. The 14th plan, the one that just ended, was about achieving breakthroughs. This one, the 15th, is all about conversion.
Conversion.
Taking those breakthroughs out of the lab and embedding them so deeply into the real economy that they become the new normal. And they're using the domestic market, this enormous domestic market, as the primary testing ground.
I saw a perfect example of this in the sources when it comes to energy. We hear green energy and we think solar panels, maybe wind turbines. But the strategy here is described as electrons to molecules. Can you break that down for us?
Yes, this is a fantastic example of new quality productive forces in action. So you have this problem. China has built an absolutely staggering amount of renewable energy capacity, mostly in the west and north of the country.
Great. Solar farms in the Gobi Desert, wind turbines across Inner Mongolia.
Exactly. But the factories in the cities are thousands of kilometers away in the east. Getting that electricity across the country without massive losses, without overloading the grid, it's a nightmare of physics.
And you can't just build a big enough battery. You can't put a gigawatt hour in a Duracell.
Not yet, anyway.
Yeah.
So the strategy is, instead of trying to move the electrons, you convert them. You use that surplus, often wasted renewable energy, to power electrolyzers that split water into hydrogen. You turn the electrons into molecules.
So you turn electricity into a gas.
And we are not talking about small pilot projects here. We are talking about nation-building infrastructure. The sources detail the North China Spine.
The North China Spine. I love these names. It sounds like something out of a fantasy novel.
It's very real. It's a 1,038-kilometer hydrogen pipeline. There's another one already under construction, a 400-kilometer line from the wind farms in Inner Mongolia straight to the industrial heartland around Beijing.
Wow.
These are qualitative shifts in how an economy is powered. This is not just building another power plant. It's a whole new circulatory system for energy.
So instead of sending the electricity down a high-voltage wire, which has resistance, it loses energy over distance. You turn it into hydrogen gas, you pump the gas through a pipe, which is much more efficient, and then at the destination, you can either burn it for industrial heat or run it through a fuel cell to turn it back into electricity.
Exactly. You're moving energy the way we've moved oil for a century. But it's clean hydrogen. And here's the kicker. It turns the energy grid into a physical inventory.
What do you mean by that?
You can't store electricity in a wire. It's use it or lose it. But you can store hydrogen gas inside the pipeline itself. You can pressurize it. If the sun doesn't shine or the wind doesn't blow for 3 days, you don't care. You still have days' worth of energy sitting in the pipe ready to go. That's resilience.
That is a game changer. And it seems like this whole philosophy of focusing on, real stuff over virtual stuff is bleeding into finance too. I saw a really fascinating angle in the plan about where money is allowed to flow.
Oh, the crackdown on the quant funds.
Yeah, let's talk about that. Because in the West, high-frequency trading, algorithmic quant funds, they're basically the kings of the market. They are the market in many ways. China seems to have gone hard in the opposite direction.
Hard the other way. Through 2024 and into 2025, we saw a systematic crackdown on quantitative hedge funds, the big algorithmic traders.
Yeah.
The number of major funds was actually forced down from 32 to 30, and their trading volumes were heavily restricted.
Why?
The government's message was explicit. We do not want capital playing casino games in the stock market. They see it as purely speculative and destabilizing.
So they want the money in the factories, not in the algorithms that trade stocks in microseconds.
Precisely. And you contrast that with what they're promoting, the ECNY, the digital yuan. By the end of last year, transaction volumes were hitting 14 trillion yuan.
Which is a lot.
It's a huge number.
Right.
And the goal there is to build a financial system that is transparent, controllable, and directly serves what they call the real economy.
Manufacturing, tech development, infrastructure.
Not speculative finance. The philosophy is very clear. It's a very directed form of capitalism. The state is essentially saying, you are free to innovate and make money, but you have to make things to do it.
Make real things. And there is no better example of making things that are about to change the world than our next topic, the battery revolution.
Yes.
I am so excited for this one. I feel like we've been promised solid-state batteries for, a decade? It's always the technology that's just 5 years away.
It's been the classic vaporware of the EV industry, always just over the horizon.
It was. But it seems like the horizon is here.
Hmm.
So tell us what is happening in July of this year, 2026.
In July 2026, China's national standards body is officially releasing the first ever national standard for solid-state batteries.
Okay, why is a standard such a big deal? I mean, usually the tech comes first, then the standards body catches up and writes the rules. Why is this so important?
Because for years, the term solid state has been abused. It's been pure marketing. Companies have been selling what they call semi-solid or jelly roll batteries and hinting that they're solid state to get a bump in their stock price.
Right, it was all just marketing fluff.
Total fluff. It created enormous confusion in the market and for consumers. This new standard creates a hard, non-negotiable technical boundary. It puts an end to the ambiguity.
It's the official litmus test.
It is, almost literally. The core of the standard is a thermal runaway test, a 120 degrees Celsius heating test.
Okay, so you cook the battery.
You cook the battery, and if the battery cell loses more than 0.5% of its total mass during that test, you are not legally allowed to call it an all-solid-state battery in the People's Republic of China, period.
Wait, walk me through the physics of that. Why does losing mass when you heat it prove that it's not truly solid?
Because liquid electrolytes evaporate. The liquid part of a traditional lithium-ion battery, or even a semi-solid gel battery, will start to gas off when it gets hot enough. You lose mass. A true solid-state electrolyte one, made of a ceramic or a sulfide or glass, is a solid block. It doesn't evaporate. It just sits there and gets hot.
Wow. So it stops the line.
It forces engineering honesty, and it formally splits the market into three clear categories. Liquid, which is what most cars have now, semi-solid, which is a kind of bridge technology, and all solid state.
And because China is the biggest EV market on the planet,
Their domestic standard effectively becomes the de facto global benchmark. If you're a German or an American car maker and you want to sell a car with solid-state batteries in 2027, you can bet it's going to have to pass that Chinese 120-degree test.
this isn't just a piece of paper, though. The standard is being released because the hardware is actually ready.
The hardware is ready. The sources are clear on this. GAC Group, that's a huge state-owned automaker in Guangzhou, has already finished construction of the first mass production line for high-capacity, all-solid-state batteries.
This isn't a lab, it's a factory.
It's a gigafactory. And they've solved a huge problem. They're using what's called a dry anode process.
I read about that. That's about cutting costs, right? How does that work?
Yes. Normally, making battery components is a wet process. You mix all the chemicals into this, gooey slurry. You have to paint it onto a foil, and then you have to run it through these massive, energy-hungry ovens to dry it all out.
Sounds slow and expensive.
It is. The dry process skips the slurry and the ovens. You basically just press the dry chemical powders directly onto the foil. It's way faster, cheaper, and uses a fraction of the energy. GAC seems to have cracked how to do this at scale.
And they're not the only ones. There's Dongfeng.
Dongfeng's being very aggressive. Their target for mass production is September 2026, so just a few months away. And their first-gen solid-state battery is claiming an energy density of 350 watt-hours per kilogram.
Okay, put that number in context for us. What does a good EV battery have today, like a Tesla Model 3?
So a standard LFP battery in a base Model 3 is around 160, maybe 170 watt-hours per kilogram. A really high-end nickel-based battery in a performance car might just touch 250.
So 350 is more than double the base and a huge leap over the best stuff we have now.
It's a massive jump. In practical terms, you're talking about a normal-sized sedan with the 1,000-kilometer range.
1,000 kilometers, that's over 600 miles.
Yes.
That kills range anxiety. Stone dead. You could drive from Los Angeles to San Francisco and back on a single charge.
Pretty much. And BYD, the biggest player of them all, is right behind them, targeting 2027 for their initial solid-state production. But the really wild, almost sci-fi moment in all the source material, it comes from a patent filed by Huawei.
And this is where it gets really interesting because Huawei isn't even really a car company. They're a tech and telecom company. But they have this patent for a nitrogen-doped sulfide solid-state battery.
This is the moonshot. Sulfide-based electrolytes are considered the holy grail of the holy grail. They conduct lithium ions incredibly fast, which means super fast charging.
So what are the claims in this patent?
The claims are staggering. The patent suggests this battery chemistry could enable a 3,000-kilometer driving range.
3,000 kilometers. That's almost 1,900 miles you could drive from New York to Denver without stopping.
Correct. And a 5-minute charge time.
Okay, hold on. We have to apply the reality check here. Is this actually real or is this just a theoretical patent for something we might see in 2050.
So it's a patent. That means the physics works on paper. And they've almost certainly built a small lab scale version. But yes, this is where we have to apply the big expert caveat.
Go.
Sulfide materials are, right now, incredibly expensive to produce in a pure form. There are supply chains where it costs more than gold by weight. And a battery big enough to go 3,000 kilometers would be, well, very heavy.
So we're not going to see this in a Honda Civic next year.
No, absolutely not. But what it does is it signals the trajectory. It shows you where the most aggressive R&D is heading. Even if they fall short of the moonshot and only hit 1,500 kilometers, it completely changes the entire paradigm of transportation and logistics.
And there's one more huge factor we haven't even mentioned: safety.
The big one.
Right. The reason lithium-ion batteries catch fire is the flammable liquid electrolyte. So solid state means no liquid. Does that mean no fire?
It means a vastly, vastly reduced fire risk. The solid electrolytes are typically ceramics or polymers. They just don't burn in the same way. They don't leak. This allows engineers to get rid of a lot of the heavy, bulky safety equipment inside a battery pack and pack the cells closer together.
Which in turn increases the range even more.
It creates a virtuous cycle. Better safety allows for better density, which means better range.
Okay, so we have the 15th five-year plan setting this grand strategy. We've got this battery revolution about to power everything, but none of it works without the brains. None of it works without the microchips.
Correct. And that brings us to what the sources are calling the silicon siege and the subsequent breakout.
For the last few years, the dominant narrative in the West has been pretty simple. U.S. export controls would effectively freeze China's semiconductor industry in time. No advanced lithography tools from ASML means no advanced chips. Game over.
That was certainly the intent, and it caused immense disruption. But the reality, as we look at the hard data from late 25 and early 26, is something else. It's a story of decoupling and a ferocious drive toward what they call structural self-reliance.
Let's start with what you call the workhorse breakthrough. We, in the media, we obsess over the latest 3-nanometer chip in the newest iPhone, but the rest of the world, the industrial world, it runs on older, more mature chips, right?
That's the crucial point that gets missed. Your car, your washing machine, the industrial robots in a factory, the smart power grid, they don't need 3-nanometer chips. They run on 28-nanometer chips. 28 millimeters is the sweet spot. It's a fantastic node. It has the perfect balance of performance, power consumption, and, most importantly, cost. It's the blue-collar chip that makes the modern world function.
And this is where China has had a domestic breakthrough.
A huge one. In May of 2025, SME, that's Shanghai Microelectronics Equipment, delivered their first fully domestic 28-nanometer immersion lithography machine to a production line.
Okay, immersion is the key word there. I've always wondered, what does dunking the silicon wafer in water actually do?
It's all about bending light. It's basic high school physics, just at an insane level of precision. Light refracts, or bends, when it passes from air into water. Immersion lithography uses a thin layer of ultra-pure water between the final lens and the silicon wafer. This allows the lens to focus the light into a much tighter spot than it could through air.
So you can draw smaller lines?
You can draw much smaller lines. Before this machine, the best domestic tools were stuck at around 90 nanometers, maybe 65 millimeters if they really pushed it. Breaking the 28-nanometer barrier with a machine made entirely with domestic components means China can now produce the vast majority of chips needed for its entire industrial base without any reliance on ASML or other Western tool makers.
That is a massive strategic victory for them. It secures their entire industrial economy.
It does. It effectively makes the sanctions on that generation of technology irrelevant.
Yeah.
But of course, they didn't stop with the workhorse chips. They're also brute forcing their way to the high end.
The 5-nanometer workaround, this is the one that really surprised a lot of analysts. Sembec, their biggest chip foundry, is now in volume production of 5-nanometer chips without using EUV machines. I thought EUV was absolutely required for anything below 7-nanometer.
It's the most efficient way, but it's not strictly required. The technique they're using is called multi-patterning. Think of it like this. Imagine you need to draw a very, very thin line, but your pen is too thick. So what do? You use your thick pen to draw the left edge of the line. Then you shift the paper a tiny, tiny amount and use the same thick pen to draw the right edge of the line. You've used a thick tool twice to create a very thin feature in between.
That sounds incredibly complicated and expensive and slow.
It is all of those things. It requires many more manufacturing steps, more masks, more time, and the yield, the number of good chips per wafer, is much lower than with EUV. It's a brute force method.
But the crucial point is,
It works. And we know it works because the proof is in the wild.
The Huawei Kirin 9030 chip.
Exactly. The Kirin 9030 system on a chip. It's a 5-nanometer chip. It's being mass-produced on SMIC's N+3 node, and it's in their latest smartphones. It's tangible proof that even without access to the world's best tools, they found a way to get to a modern competitive process node.
But they still want the best tools. They still want their own EUV machine. And this is where the story gets, I don't know, a little James Bond.
It does feel a bit like that, the so-called Manhattan Project for EUV.
The sources point to a very high-security lab somewhere in Shenzhen that's dedicated to cracking EUV. But they aren't just trying to copy the ASML machine, are they? They're trying a different approach.
A completely different physics path, it seems. So the ASML machines use a hugely powerful CO2 laser to blast tiny droplets of molten tin thousands of times a second to create the EUV light plasma. It's an engineering marvel, but it's insanely complex.
So what's the Chinese lab trying?
They're experimenting with what are called solid-state lasers as the light source. It's a fundamentally different way to generate that initial power.
Is it better?
In theory, it could be much more efficient. There was one specific metric in a technical report that really stood out. A lead scientist on the project, a guy named Lin Nan, published a paper claiming they achieved a 3.42% conversion efficiency in their light source.
3.42%. I mean, that sounds incredibly low. Is that good?
In the bizarre world of EUV physics, that is a huge number. ASML's own research arm has published benchmarks in experimental setups that are lower than that. It's a very strong signal that this isn't just about reverse engineering. They are exploring a genuinely novel path to the same goal. If they can make solid-state EUV work at an industrial scale, they could potentially leapfrog the current generation of technology.
It's that old saying, right? Necessity is the mother of invention. You block them from buying the tool, so they're forced to invent a whole new type of tool.
Precisely. And all this new domestic computing power, from the 28-nanometer workhorses to the 5-millimeter thoroughbreds, is being fed directly into our next topic, AI.
But again, with the twist, we're not just talking about chatbots. We're not talking about asking AI to, write a funny poem about your cat.
No. We're talking about AI with a physical body, embodied AI. This is a crucial distinction and a major focus in the 2026 landscape.
Okay, let's set the stage. There was this DeepSeek moment back in early 2025. What was that?
Yeah, a Chinese AI lab called DeepSeek released a large language model that, in benchmark tests, basically matched the performance of the very best models from Google and OpenAI.
And it was trained for much less money, I recall.
A fraction of the cost. It was a Sputnik moment for a lot of people in Silicon Valley. It proved that China was absolutely still in the AI race.
But the sources we've looked at suggest they've pivoted since then. They're not trying to win the Chatbot of the Year award. They're going for something called vertical AI.
Yes. Vertical AI means you stop trying to build an AI that knows a little bit about everything in the world. Instead, you build an AI that knows absolutely everything about one specific, narrow industrial domain.
So not an AI that can write a sonnet and also tell you about quantum physics.
No, it's an AI that knows everything about optimizing shipping routes in the port of Shanghai, or an AI that has ingested every single chemical synthesis paper ever written to design new materials. It's AI trained on specific proprietary industrial data.
To solve real-world business problems. And this leads directly to giving that AI a body.
It does. The 15th five-year plan explicitly identifies humanoid robots as a strategic emerging industry and a key future growth driver.
I love the examples in the reports here. The Zeekr factory.
Zeekr is a high-end EV brand. They have deployed humanoid robots from a company called UB Tech onto their actual car assembly lines.
So these aren't just the robotic arms you see welded to the floor in most car factories.
Not at all. These are bipedal, two-legged robots that can walk around the factory floor, work alongside human workers, pick up tools, and perform complex assembly tasks.
And what about this Walker S2 robot?
This one is amazing. The Walker S2 is a humanoid robot that can autonomously change its own battery.
Wait, really?
Yes. So it works its shift for, say, 4 hours. Its internal monitor says the battery is at 10%. It stops what it's doing, walks over to a charging station, pulls out its depleted battery, slots in a fully charged one, and then walks back to its station and then resumes its task.
That's a 204/7 workforce. It's incredible. And also, slightly terrifying.
It's the solution to a huge demographic challenge. China's population is aging rapidly, and the human workforce is shrinking. They see robotics not as a luxury, but as a demographic necessity to keep the factories of the world running.
And it's moving beyond just factories. I saw a note about a company called Unitree Robotics launching a humanoid robot app store.
This is a brilliant business strategy. They're treating the robot like a smartphone. You buy the generic hardware, the robot body, and then you go to their app store and download the specific skills you want it to have.
So you could download a barista app and it learns to make coffee.
Or a warehouse logistics app or a fold the laundry app. It turns the hardware into a platform, which is a much more scalable business model.
And then there's the boring AI that's probably making the most money, the stuff being done by Alibaba and SF Express.
SF Express is basically the FedEx of China. They move billions of packages. They've rolled out what they call AI mode for their logistics network. Sounds dull, but it's an AI that constantly optimizes every single delivery route in real time. Shaving even 1% off your fuel costs and delivery times when you operate at that scale is worth hundreds of millions of dollars.
It's AI as pure infrastructure.
Exactly. And the last stat on this, the one that really blew my mind, was in drug discovery. As of the first quarter of this year, Q1 2026, Chinese firms and institutions accounted for 70%. 70 of all global patent filings for AI-driven drug discovery.
70%. That's not just leadership, that's dominance.
It's complete dominance, and it goes almost entirely unnoticed in the public discourse. While the West is having endless debates about AI art generators, they're using AI to simulate molecular interactions to invent new life-saving medicines. It's that ruthless, one-to-one focus on application again.
So we've got the strategic plan, the new energy, the chips for brains, the robotic bodies. Now we look up. The high frontier.
Space. The ultimate high ground, strategically.
And late 2026 is slated to be a very busy period. It starts with the Cheney 7 mission to the moon.
This is an incredibly ambitious and important mission. It's not just another flag-planting trip. It's heading to the moon's south pole, to a specific spot called the Shackleton Crater.
And why there? What's so special about the South Pole?
Water. That's where the water is believed to be, frozen as ice in the permanently shattered floors of the deep craters where sunlight never reaches.
And Cheney 7 is a complex mission. It's not just one spacecraft.
No, it's a whole fleet. It has an orbiter that stays in high orbit, a lander that touches down on the crater rim, a traditional solar-powered rover to explore the sunlit areas, and the coolest part, a mini-hopping probe.
A hopper? What, like a pogo stick?
More like a drone, but since there's no air on the moon for propellers, it uses small thrusters to hop or fly short distances.
And what's its job?
Its job is to do what the rover can't. It'll actually fly off the lander and hop down into the pitch-black, permanently shattered part of the crater. It has its own lights and instruments to sniff for direct evidence of water ice, and then it will hop back out to the lander to transmit its data.
That is some seriously bold engineering.
And the goal is very clear. This is all preparatory work for the planned International Lunar Research Station, the ILRS. You can't have a permanent human base without a local source of water. Change 7 is the prospecting mission.
And while that's happening at the moon, back here in Earth orbit, the Tiangong space station is getting a major upgrade.
It is. It's getting a new neighbor. The Zhenjian Space Telescope is scheduled to launch in late 2026. This is a Hubble-class observatory, but with a field of view that's 300 times larger than Hubble's.
So it can map the sky much faster.
Much faster. But here's the really clever part. It doesn't fly off on its own. It's designed to co-orbit with the Tiangong station.
So it just flies alongside it.
Exactly. And if it ever needs repairs, refueling, or a scientific instrument upgraded, it can perform an automated rendezvous and dock with the space station.
Mm-hmm.
The taikonauts can go out, perform the maintenance, and then it undocks and goes back to work.
That's brilliant. It solves the biggest problem with space telescopes like Hubble or JWST.
Yeah.
You can't fix them if something breaks.
It makes the entire system sustainable. And below them, you're seeing the rise of a commercial space sector. Companies like Deep Blue Aerospace and iSpace are slated to do full demo flights of their reusable rockets in December. They're building their own SpaceX-style competitors to crash the cost of getting to orbit.
Okay, and for our final topic, we have to talk about quantum. This feels like the technology that ties everything else together, from space to Earth.
It is perhaps the most strategically significant technology of them all because it's about information security. As of right now, China has an operational, secure quantum communication link running from Beijing to, of all places, South Africa.
How does that even work across that distance?
It uses a dedicated satellite called Jinan-1. The satellite facilitates what's known as quantum key distribution, or QKD.
All right, break that down for us in simple terms. Why is QKD so much better than the encryption we use for, say, online banking today?
Because the encryption we use today is based on math. It relies on a mathematical problem being too difficult for a classical computer to solve in a reasonable amount of time. But a powerful enough supercomputer, or critically a future quantum computer, can eventually solve the math and break the code.
Okay.
QK is not based on math, it's based on physics. It uses the quantum state of individual photons to transmit the encryption key. And according to the laws of quantum mechanics, the very act of trying to observe or eavesdrop on those photons will inevitably disturb them and change their state. The signal collapses.
So it's not just hard to hack, it's physically impossible to hack without being detected instantly.
It's hack-proof by the laws of nature. And the sources say they're now working on integrating the satellite QKD directly with their terrestrial 5G networks, creating a seamless, ultra-secure communication bubble.
And on the computing side of quantum.
The latest machine's called Zhuangzi 3.0. It's a 105-qubit superconducting quantum computer, and they're making credible claims of quantum supremacy.
Which means?
It means performing specific, highly complex calculations in a matter of seconds that would take the world's most powerful classical supercomputers thousands of years to complete.
So we have covered a ton of ground here. Let's try to bring it all together. Batteries, chips, robots, space, quantum. What does this all mean for the listener? What's the big takeaway?
The big takeaway is that the meaning of the China price has fundamentally changed.
How so?
For 30 years, the China price meant one thing: cheap labor. Companies moved manufacturing to China because it's cheap to hire people to assemble things. That era is over. The new China price is about the efficiency of these new quality productive forces.
It's not about cheaper workers anymore. It's about smarter factories, cheaper energy, and fully autonomous supply chains.
Exactly. It's about the high-tech efficiency that comes from robotics and AI integration. And for any global company, this creates a massive black box risk.
A black box risk.
You simply cannot afford to treat China's domestic technology ecosystem as a mystery anymore. The global technical standards for the next generation of EV batteries are being written and tested there. The playbook for integrating humanoid robots into manufacturing is being written there. If your company isn't paying obsessive attention to what GAC or SMIC or UBTech is doing, you are flying completely blind into the next decade.
It really feels like the technological center of gravity, for industrial tech at least, has shifted.
It absolutely has.
I want to leave our listener with one final provocative thought to chew on. We talked about that quantum network.
The quantum-safe Silk Road.
That's the phrase. Just think about this for a second. The West, led by the U.S., spent decades and billions of dollars laying the physical infrastructure of the modern internet, the undersea fiber optic cables that connect the continents.
We control the pipes.
We control the pipes. But what China is now offering to the global south, to nations across Africa, South America, Southeast Asia, is a completely parallel communication network, one that bypasses our pipes entirely, using their satellites and the unbreakable laws of quantum physics.
It's a completely different architecture for global communication.
So the final thought is this. The race isn't just about who builds the fastest computer. It's about who builds the fundamental infrastructure of the 21st century.
But right now, on multiple fronts, the construction crews are very, very busy.
That's all we have time for in this deep dive. Thanks so much for listening.
Stay curious.